You had 10 minutes to think about a relationship between lambda 0 and lambda. So basically, lambda 0 is the wavelength in vacuum. Lambda is the wavelength in material. Okay? So given the fact, you know that the speed of wave in material will be always slower than in vacuum. So also lambda will be smaller than or equal to the wavelength in vacuum. Okay? Another way you can write is directly divide this two. So basically the ratio of C to V will be equal to lambda 0 to lambda. Okay? This will become useful for the first part, transmission line. Okay? A lot of students would come up and ask me, what does the wavelength mean? Okay? So later I will talk about it. Your ability to understand wavelength is extremely important. So I'm going to try to convince you. Learning electromagnetics with transmission lines as a starting point is the best choice. Okay? So I'm going to use the following 3 slides to convince you. After my introduction of these 3 PowerPoints, I'll do a survey. Okay? So again, V equals frequency times the wavelength. So these are the waves in materials. The way we analyze electromagnetic problems are actually frequency dependent. What do I mean? Frequency is denoted by F. So if you have a very low frequency source, meaning F is very small, what is going to happen to the corresponding wavelength? When F is very small, lambda has to be very long, right? Okay? So in the past, try to think. Most of you just passed electric circuits, which you hate also. It's a mandatory course, 电路学. You all passed it, but you all hate it. So in electric circuits, you learned resistors, capacitors, and maybe inductors, L. Okay? R, L, C. It's all you learned in one semester. But try to think back how you learned R, L, and C. If you're given a resistor, you basically only care about its voltage drop, right? And its current. So once you have a steady state current flowing across a resistor, it will introduce a voltage drop, right? So that voltage drop is V, and the current flowing across it is I. But do you know how precious it is for you to be able to formulate that equation? You learned this relationship starting from high school, I, R times R, right? The reason you can write this down so easily is because in the past, you all assumed this operational source is of extremely low frequency. So what do I mean by that? If your frequency is low, then your lambda is very long, right? So if your frequency is high, then your lambda is very short. Okay? So what is going to impact this solution form? For example, I have a resistor. Usually for resistors, you have some kind of color coding, right? So when you buy a resistor, you have certain given physical dimension. And that physical dimension is listed here, D, right? When you buy a resistor, it's probably 1 centimeter long, okay? And then you have to ask a question. C equals, or V equals F times lambda. So in terms of space, I'm trying to plot the wavelength information for you. So this is one wavelength for a given frequency, okay? So then you have to ask, for example, in this case, when your operational frequency for that source is very low, then the wavelength is very long, right? So that means across the entire resistor, point by point, all the voltage values are the same. Let me move to this case. Let me erase this one, and let's focus on this case. If the frequency is so high, so the wavelength is so short across the length of a given resistor, you already have some kind of voltage change as a function of distance. In that case, are you able to analyze this simple circuitry using whatever you have learned? Can you still write VR equals IR times R? At this location, what is the voltage value? 0, right? 0 means current has to be 0, right? So in any case, if your operational frequency is high, making your wavelengths very short, across a single element, you have to worry about the voltage values and maybe the current values. Both are being position dependent. And that's something you never learned, okay? So in the past, in electric circuits, you always assumed, do you still remember hearing this terminology? Lumped circuit element assumption. In the first chapter, for every electric circuitry textbook, it would tell you the first assumption being made was you're working in the lumped element assumption. And students don't understand what that means. That means your device dimension, the length of your device, resistors, capacitors, inductors, as compared to the operational wavelength, are extremely small. So that across the entire device, voltage and current can be viewed as a constant. Otherwise, you don't know how to analyze it, okay? So you only have to analyze V as a function of time, I as a function of time, but you don't have to worry about the spatial dependence, okay? So lumped element assumption means your operational frequencies are extremely low. For example, the electric power that we're using from Tide Power, operational velocity is still the speed of light. In vacuum, or wave in vacuum, 60 hertz times lambda. Try to do a calculation. What is the resulting wavelength? Huge, right? Extremely long. So that means when Tide Power is generating some kind of current or voltage, entire Taiwan is seeing the same voltage value, right? The length of Taiwan is only 400 kilometers, so probably you don't really care, okay? So in the past, you analyzed simple circuitry using resistor, capacitor, inductor, and you all assumed the voltage and currents are constant in terms of space domain. That's because your operational frequencies are extremely low. The mathematical tool that you need is just ordinary differential equations, but you don't want to remember that, right? But you have to do partial differentiations, but only in time. So that's simple. Now, as you can see, the study of electromagnetics is to enable you to learn everything with no frequency constraint. Meaning, in this equation, frequency can start from 0 to infinite. Meaning the wavelength can also start from infinitely long to almost 0, right? Whatever you learn should cover everything, all the frequency range. So now, in certain case, if the device dimension is still very small as compared to the wavelength, but the delivery length is quite long, greater than the wavelength. Do you know how to analyze this kind of problem? You don't, because you don't have the adequate tool in the past. What do I mean? For example, United States is very big, right? If you have a nuclear power plant built in LA, and you want to deliver the power to New York, that's probably 5,000 kilometers. So you build some wire. You have copper wires connecting Los Angeles to New York. And you deliver the power to New York. Of course, you want to charge them, right? But somehow along the way, when you move along the line, maybe Kansas, Chicago, the voltage values would change because the operational wavelength is actually shorter than the length of your copper wire. So this means point by point, your current value is changing, your voltage value is also changing. So the parameter to be analyzed, voltage as a function of time, but also as a function of space. Current now also becomes a function of time and space. So basically, your partial differential equations would involve time and space. So this is more complicated, but still, you can manage it because the good thing is both voltage and current are scalars. So at this moment, what's the difference between scalar and vector? Most of you don't really know. You don't know the difference, so you don't know how nice I am to start this issue, the class, with transmission line. Scalars only have values. They don't have directions, right? Scalar voltage equals 1 volt. That's scalar, right? And your weight is probably 75 kilogram. That's scalar, okay? But velocity, whenever you have this vector sign, means you might have 1, 0, minus 100, right? In different directions, okay? So whenever you have vectors involved, things become complicated, okay? So let me assure you, for all the problems that you will encounter later after transmission line are all involving with vectors. Electric fields and magnetic fields, they are both functions of x, y, z, and time. So each field, they have 4 different parameters. That means complication. So instead of jumping into vector analysis and teaching you everything using difficult vectors, let's start with something simple. Something that you already know, even though you have a very long distance, but still, we can formulate or effectively find an equivalent circuit model using the lumped circuit elements that you learned before in electric circuits. We can model such transmission line using resistors, capacitors, inductors. Okay? So that I view as a connection between lumped element circuit to electromagnetic waves. From low frequency to extremely high frequency, somewhere in the middle, we try to establish the mathematical tools that we need and the physical insights that we need. Okay? So this is a better connection. So are you all convinced? To start with transmission line is the right move. And you picked the right class to start with. But really, I mean, for all these geometries, when your operational frequencies are extremely high, so that your device length, diameter, and length are all beyond the wavelength, all the calculations are extremely difficult. So if you ask my students, they don't really solve the problems using hand. They run computer simulations. The only possible way is to run computer simulations. And sometimes you have to spend maybe 2 or 3 days with one problem. Okay? So they can have excuse, not doing anything. This is running simulation. Background information. Now, this is where I need your inputs. Do you still remember the wording, the terminology, phasor representation? Phasor. Does it ring any bell? Do you still remember? Phasors. If you still remember phasor, you don't know what phasor means, but you remember the wording phasor, raise your hand. Yeah, being a professor in Taiwan, always ask the right question. When you hear the wording phasor, you don't remember it, raise your hand. Okay, you all remember it. What does phasor mean? To my best knowledge, you learned about phasors at least twice. One time is in electric circuit, just the semester you just ended. And maybe another time in calculus, probably. Right? So you at least learned phasors twice already. So why do I need to bother for the 3rd time? I don't. I just want to use maybe 3 minutes. Phasor representation is a mathematical tool. That's how you learned in the past. But today I want to tell you what does it mean physically. Okay? So again, let's start with math. You have a time varying function. So for example, you have a voltage as a function of time. You have the amplitude, the maximum value you can ever achieve, and its oscillation in time follows the cosine relation. Okay? Omega is the frequency, the angular frequency, 2 pi times f. So omega equals 2 pi times f. Okay? So what does this phi stand for? If you don't understand the meaning of phi, there's no way you can ever understand about phasor. So how can you help yourselves to review this phasor, which will follow you and haunt you probably for the rest of your life? So it's better for you to understand it now. Really. If you decide to work in the science park in Hsinchu, You probably still need to understand it. Okay? So what does it mean? What is the meaning of this phi? Cosine omega t plus phi. So what does it mean? I'm trying my best to draw a cosine. Okay, that's quite beautiful to me, in my personal opinion. Okay. For the cosine I drew on the blackboard, what is its phi value? Oh, you have to think. I mean, how can this guy just ask me this question? If this is showing up in your first examination, do you like it? Would you like me? You would love me, right? It's 3 point. So, for this given cosine wave in time, at time equals to 0, you have the maximum value. So what is the value of phi? Answer me, loud and clear. Is it from the TA or? 0, right? 0. Does everybody agree? 0. So for this case, phi equals to 0. Does everybody agree? Okay. So you only get 50% of a point. The TA, how many points would you give? Both TAs. This is trying to ask you, I'm trying to reveal your understanding towards time-dependent periodical function. Cosine is periodical, right? Since cosine and sine, these trigonometry functions are periodical, how can you define phi equals 0 or 2 pi or 4 pi or whatever, integer multiple of 2 pi? So the correct answer to this is right? M being an integer, 整数. Okay? So basically, you have some kind of preliminary understanding to the meaning of phi. So can anyone, I shouldn't do this because starting from Wednesday, you won't be here. My fear is you think this class is so interesting, more people are actually attending starting on Wednesday, which is not my hope. Okay? So, what can I do to generate a new cosine with the same frequency, but only a translation in time? How can I shift this entire thing on the time dimension without changing the amplitude, without changing the periodicity? I am going to draw something like that. Okay? For the yellow trace, how should you represent its face value? Again, the same question. Are you going to like me or hate me if that question appears on your examination?